or electron geometry for short. When we have an octahedral electron geometry, then we have a lot of different molecular geometries, depending on how many lone pairs there are. And so if there are no lone pairs, we'll have all bonded pairs, and the molecular geometry will be octahedral. If there's one lone pair, then normally what's done with the one lone pair is you put it on the bottom. And so what you end up with is a shape that looks like this. And we call this one square pyramidal, because it forms a square-based pyramid here. So square pyramidal or square pyramidal. When we have two lone pairs, then we have a choice what to do with the second lone pair. We could put it in one of these adjacent sites, which is 90 degrees relative to the first lone pair. The first lone pair is in this site here. Or we can put it in the opposite site, which is 180 degrees. So should we put the two lone pairs 180 degrees apart or 90 degrees apart? 180. And so it doesn't matter which of the sites you pick, the opposite will be for the electrons. And so we end up with a structure that looks like this. This structure here is called square planar. If we have three lone pairs, then we'll just pick another one of these sites here. Let's maybe bring it out here so it's projecting out. Then we'll have this one, and this one here. And it might be hard to see, but this is T-shaped. So it's another T-shape. We saw T-shaped in trigonal bipyramidal as well, but in this case we have three lone pairs, and then we have this which forms the top of the T, and this which forms the base T. If we have four lone pairs, then how should we do it? Turns out with four lone pairs, what we're going to end up with is the case where we'll put those in equatorial-like positions here, and we'll have the axial. And then this comes out linear. So we have a lot of different molecular geometries for octahedral, just depending on how many lone pairs we have. All right, maybe we'll look at some examples of these later on. But for right now, I want to go back to this topic of greater than an octet and look at some other scenarios. So the scenarios with the trigonal bipyramidal, we hybridize a d orbital and end up getting sp3d2. And for octahedral like this, we hybridize two d orbitals to get sp3d2. And so one is the d orbitals get incorporated into the hybrid scheme. And so sp3d will have 1, 2, 3, 4, 5. sp3d2 will have 1, 2, 3, 4, 5, 6. But we can have d orbitals participate in the bonding too. And this is going to be called pd pi bond. And it's an alternate way that we can expand an octet. And so a classic example of this would be this OPCl3. This one's called phosphoryl chloride. And we have oxygen with 6 electrons, phosphorus with 5 electrons, and 3 chlorines with 7 electrons each. So that's going to give us 21 electrons. And so so that's 27, 32 electrons altogether. We come up with the Lewis structure for this. We'll probably put phosphorus in the center. We'll bond this to an oxygen and chlorine. Then we'll complete the octet to the oxygen here first, and then the chlorines. And we use up all 32 electrons here. And so this structure looks pretty good, except for one thing. What doesn't look good about this structure? The octet looks good.
The formal charge.
Right, the formal charges. Let's take a look at the formal charge. What's the formal charge on this oxygen? And the formal charge on phosphorus? Plus. And so that's the only thing that doesn't look good. The chlorine has 0 formal charge. And so some people said, well, I don't like that formal charge. So is there a way to get rid of that formal charge? There is actually a way to get rid of the formal charge. What we'll do is we'll just take a bonding, or actually not a bonding, we would take a lone pair off the oxygen and convert that into a bonding pair here. So if we double bond the oxygen, then what does that do to the formal charge? So if we double bond the oxygen, then the formal charge goes down to 0. But the problem is now we have more than an octet. We have 2, 4, 6, 8, 10 electrons. So this is good. This is an octet. And this has an expanded octet. Normally when we have an expanded octet, then we'll just hybridize d orbitals in there. But we look at this, what is the hybridization on phosphorus in this molecule here? The hybridization on this phosphorus is sp3. Shouldn't it be sp3d? No, it's not sp3d, because in order to be sp3d, we need 5 different groups. In this case, we only have 4 different groups, 3 single bonds and a double bond. In order to be sp3d2, we would need 6, but we only have 4. With only 4 here, it's sp3d. And if it's sp3d, then let's take a, not sp3d, it's only sp3. So this is phosphorus, and it's sp3, which means we're going to have 4 equivalent sp3 orbitals. Okay, let's fill these with electrons. When we fill this, do you see any lone pairs on phosphorus? No. And so I can't pair up any of these. So does that look okay here? What's wrong with this diagram here?
That's 5 bonds. There can only be 4 there.
Yeah, this would only make 4 bonds. And number 2, what's wrong with this is how many electrons does phosphorus have in this structure? Excuse me. In this structure it has 1, 2, 3, 4, 5. Over here I only have 4 electrons. So where's my 5th electron? Well, these came from the 3s, p3. So should I stick the 5th electron in my 4s orbital? Should I just throw it in the 4s? Okay, no. Then how about the 3ds, which are even higher in energy? Should I put the 5th electron in the 3d? And the answer is yeah. That's where the 5th electron goes. It's going to go in the 3d. Now I have all 5 electrons. And so I'll have to figure out what the bonding is next. So figuring out the bonding here, what is the hybridization on chlorine here? That's sp3. So I'll have an sp3 chlorine come in. All right, that's fine. I'll bring in the chlorine here, which is the sp3, and bond it here. and then another chlorine here, and another chlorine here. That takes care of my 3 chlorines. And then I have to do something about the oxygen. So when I look at the oxygen, let's take a look at the oxygen here. What is the hybridization on that oxygen? sp2. And we know that when we have oxygen as sp2, there are 3 sp2 orbitals here. Are there any lone pairs on the oxygen? Yeah, there are 2 lone pairs. So we'll put those in 2 of the sp2 orbitals. And then that singly occupied one, actually let's do spin down here, can bond. So here, this oxygen sp2 can come in here to the phosphorus sp3 and form a sp2 sp3 sigma bond. Okay, are we done there? No, we're not done because how many electrons does oxygen have? 1, 2, 3, 4, 5, 6. How many did I put in here? 1, 2, 3, 4, 5. Where does my 6th electron go for oxygen? Yeah, it's going to go into a p orbital, which is unhybridized here. And so I'll put 1 there. And so the oxygen is going to double bond. We're going to take the sp2 electron and form an sp3 sigma bond, and then we're going to take the p electron here and form a pi bond. So this is going to be a sigma bond here. This is going to be a pi bond here. But this pi bond is going to look a bit different. In other words, from oxygen's perspective, phosphorus is going to come in here, and phosphorus is going to bond its sp3 electron here. And so this is my sigma bond here. And then this phosphorus does it have a p orbital that can form a pp pi bond? No, it has a d orbital. And so that d orbital is going to come in here and form a pi bond here. And so what we form is something called a PD pi bond. Let's just look at the PD pi bond in profile. A d orbital has this kind of cloverleaf shape like this. And so this would be one of the d orbitals. Here. A p orbital will be like this. So we'll put this as phosphorus. We'll put this one as oxygen here. And what we see here is there's going to be overlap here and here. And this is pi overlap because when I look at the internuclear axis, the nucleus is here and here. There's no overlap within the internuclear axis. Like this normal region. And what we see here is we see overlap occur only on half of the d orbital lobes. So it'll be something like this. We have overlap here. Oxygen is more electronegative, but I'm going to distort the cloud. And here. So there's increased electron cloud density here and here, and that's going to hold the 2 nuclei together. So we call this a PD pi bond, or DP pi bond. In this case, maybe I should call it a DP. The D's on the left here and the P's on the right. Okay. So what I'm going to do is I'm going to just draw out the structure for phosphorochloride. Throw phosphorus here, and then it's sp3 hybridized. So I'm going to draw one sp3 orbital like this, and another one like this. So I draw two in the plane at 109 angle. And then one's going to come out, and one's going to go in. All these are at 109 angle. Each of these I'm going to fill with one electron. Like this. Here. So here are my four sp3 orbitals. Three of these sp3 orbitals are going to have chlorine come in. And the chlorine is also going to be sp3. Now, what is smaller, chlorine or phosphorus? Take a look at the periodic table. Which one's smaller? Chlorine's smaller. And so I'm going to try to represent this by the chlorine sp3 orbital is going to be a little bit smaller. So this is going to be my sp3 sigma bond with chlorine. And then the other three sp3 orbitals are going to have lone pairs. This gets kind of messy. And then one back here. There's one back here. We'll just kind of show it kind of blurry. And then I'll have my oxygen. Up here. All right, for oxygen, it's sp2. Should I draw that orbital smaller or bigger, or about the same size as the others? Which one is the smallest of the three? Phosphorus, chlorine, or oxygen? Oxygen. Oxygen is second shell. It's going to be a lot smaller. Phosphorus and chlorine are both third shell. And so if I'm only dealing with second shell, it should be pretty small. sp2. And it's sp2 hybridized, so we're going to have three sp2 orbitals in a trigonal planar arrangement like this. I'll have two lone pairs and then one bonding pair here. So here's my sp2 sp3 sigma bond to phosphorus. My sp2 to sp3 sigma bond to phosphorus. Now I need to show the pi bond. And so this is the top view. And so the top view is going to have a p orbital that we're looking straight down on. So one of the lobes, so this would be the top view here. We're looking straight down on it. And this would be the side view here, if we're looking at it in profile. So we're looking at a top view here. And so we're going to look at the d orbital and like that as well. So the p orbital, we're just seeing the top lobe here. The d orbital, we should see these two top lobes, and then these two bottom lobes should be superimposed on that. And so let me see what color I'll make that. This color. Sorry to use blue. Purple. So I'm going to make a lobe here and a lobe here. And these two lobes are going to project out. So what I'm looking at are these two top lobes here. This lobe here, this lobe here. The lobes underneath are hidden. And so I could dot those here. Yeah. And then I'm looking at the bond here. Between them. And so the pi bond here is going to connect to PD. So this will be my PD pi bond here. So what I'll do is I'm going to rotate this. So I'll look at an axis like this, rotate it 90 degrees to put the p orbital and the d orbital in profile. So if I do that, then the oxygen's here, and I'm going to twist this so that the p orbital now looks like this. So this will be the side view here. And what's going to happen to the sp2s? Well, one sp2 is going to stick out. So this is not perfectly at 90, but we're looking at it slightly from a slight angle here, so we can see this. This lobe now here is going to stick out, and this lobe here is going to stick in like this. And so these are the sp2s here. And then this sp2 just stays the same position. Okay, then we have the phosphorus here. This will be the sp3 on the phosphorus here. So what we're going to do with this is we're going to make the d orbital profile now. And so that's one d orbital here. And we're going to get orbital overlap here and here. So as far as the sigma bond goes, this is sp3, this is sp2. So I'll have my sp3, sp2 sigma bond. And then this is my p, this is my d. And so I'll have a d, p pi bond here. Okay, then I have the remaining sp3 orbitals. So if I twist this 90 here, then this one should be in the plane. So that's going to flip the side here. This is sp3 in the plane. And then I'm going to have one coming out and one going in. And then I can attach the chlorines to this. We'll just say etc. Maybe we'll just omit this here so it's a little bit clearer. And I'll just say etc. from here. There's more to it. Okay, so all I'm showing are the sigma and the pi bond from phosphorus to oxygen. So that's a PD pi bond. So it boils down to this. Actually, I'm not When we draw Lewis structures, we don't have to draw them as accurate depictions of the shape, unless you're asked to draw wedge dash diagrams. And so what this means is that sometimes people get the bond angle confused. What is the OPCL bond angle here? It looks like 90 degrees. Is it 90 degrees? No, it's not. The OPCL bond angle is actually 109. However, it's going to be distorted a little bit. It's going to be distorted a little bit because this is a double bond. These are single bonds. Double bonds have more electrons. And therefore, double bonds are going to have greater repulsions. And so if the double bonds have greater repulsion, it's going to compress these angles down. So the CLP-CL angle will be compressed to about what?
107.
107. And the OPCL angle will be expanded. Actually, that's 109. This is going to be expanded to about 111. Here. When we look at this, this looks like it will be undistorted, correct? It looks like it's going to be undistorted. This is all single bonds, and you would be correct. However, there's more than one bond to the oxygen. The oxygen has a negative charge, the phosphorus has a positive charge, and so this is like a pseudo double bond, or it's kind of like a double bond. Is there a plug there?
Yeah,
Okay.
I can do it.
Okay, thanks. The battery's gonna die. What I mean by that is this. What kind of bond is this? Can you just look at it and tell me what kind of bond that is? What's the hybridization on this oxygen here? sp3 is correct. What's the hybridization on this phosphorus?
SP3.
sp3. So this is going to be an sp3 sigma bond right there. That's one of the bonds. The other bond is this. The other bond is, this is a negative and a positive. When we have a negative atom attracted to the positive atom, that's what we call an ionic bond. And so this is an ionic bond here. So the overlap of the two sp3 orbitals is going to create electron cloud density here, which holds the atoms together. But the ionic bond here, that is the attraction between the positive phosphorus and the negative oxygen, also pulls the atoms in together. And so this is shorter than a normal phosphorus-oxygen single bond. And so it's a double bond, sort of. It's sort of because people don't call it a double bond. But essentially it's a double bond. Because when we compare it to a normal phosphorus-oxygen bond, a normal phosphorus-oxygen bond would have no formal charges, let's say. So this bond is what we say longer and weaker. This one is going to be shorter and stronger. We don't normally show ionic bonds here, so let me put those in like quotation marks. We just show the charges adjacent to one another. And that would constitute a bond. Over here, double bonds are shorter and stronger than single bonds. So we're going to have a higher concentration of charge density in this region, which results in the greater repulsions. And so the question comes up, should we just go and have and obey the octet rule and live with the formal charge? Or should we minimize the formal charge? When we look at this structure, there's no formal charges, so that's something that's nice. But expand the octet. And so which is better? So which is better historically has been to expand the octet. So when you look at 99% of the structures on Google, they're this. 99% of the structures on Google. This. It's very rare that you see somebody write it out like this. So that carries on to other common, almost phosphoryl chloride's not that common, but let's look at some common molecules and ions. For example, H2SO4. If we do this, do the hydrogens, let me ask you this, do the hydrogens bond to sulfur or oxygen? Oxygen. How could you tell that the hydrogens aren't bonded to sulfur?
Acidic hydrogens always bond to the most electronegative.
Yeah. The acidic hydrogens always go to the most electronegative, which would be oxygen. Another way you could tell is the way it's written. If it were written SH2, then the hydrogens are bonded to sulfur. But it's not. Written H2S. Well, H2S could have hydrogens bonded to sulfur, but if they're more electronegative elements, we're going to bond it to that. And so we do a Google search for the Lewis structure for sulfuric acid, and we get this. So we look at this one. This is what we call an expanded octet. It has 2, 4, 6, 8, 10. So we expanded the octet by 2. If we look at this one, how much did we expand it by? 2, 4, 6, 8, 10, 12. 12. A normal octet's 8. And so it's quite expanded. So is it okay to expand the octet so much? Well, maybe, because if you look at the formal charges are all 0. Versus this. If we didn't expand the octet and we left it as an octet, we'd end up with this structure. So this has the octet rule obeyed. Now, is it just a rule with lots of exceptions, or is it kind of a law with minimal exceptions? Well, it seems that it's just a rule with lots of exceptions. If you go on to Google, you know which is much more common? The left structure or the right structure? The left structure. If you go on to Google, it's like 99% of the structures look exactly like this. 2 double bonds. Yeah. Nobody likes this structure. Nobody. You know why people don't like this structure? The formal charges are kind of high. Oxygen's not that high. I mean, that's minus. But take a look at the formal charge on sulfur. What is the formal charge on sulfur? plus 2.
Sounds like you took pity on it.
That's kind of high. And so a lot of people will say, these formal charges are too high. I'd rather just expand the octet. But how are we going to expand the octet in sulfuric acid? So let's take a look at the orbitals here that we have available. And so the first thing when we look at the orbitals is we have to figure out the hybridization on each. What is the hybridization? So let's take a look. What's the hybridization on sulfur here?
SP3.
SP3. Okay, so we go over here and we're going to analyze the first structure here. This one. So this is sulfur with 0 formal charge, and it's SP3. 1, 2, 3, 4. So we'll have 4 SP3 orbitals. Those 4 SP3 orbitals will have any lone pairs, no lone pairs. They're going to be all bonds. And so we've used up 4 electrons here. Actually, but we don't have 4 electrons. How many electrons do we have? 6. So I need space for 2 more electrons. Well, I don't have any p orbitals here, so where do I go next? Do I go to the 4s? These are the 3 sp3s. No. I'm going to skip the 4s and go all the way to the 3d. And so 1, 2, 3, 4, 5, 6. So now I have 6 electrons. Let's take a look at these oxygens here. This oxygen, the bridging oxygen, what's the hybridization on that?
SP3.
SP3. We have 2 of those. And so we're going to have an SP3 oxygen come in here and bond. And then another SP3 oxygen comes in here and bonds. So that takes care of the bridging oxygens here. And then we have the terminal oxygens. What's the hybridization on the terminal oxygens? SP2. And so this is what must happen with those oxygens here. So an oxygen with an sp2 is going to come in here and bond. And so it's going to form an sp2, sp3 sigma bond. But when we have an sp2 oxygen, you probably already know, an sp2 oxygen will have 3 sp2 orbitals and 1 unhybridized p orbital. And then those oxygens both have 2 lone pairs, and we have 6 electrons, so it's going to fill up like this. These have to be spin down in order to pair those with phosphorus. All right. And so I got a p orbital here with an electron that can be shared, and that's going to go into this. And you know what we call this? We call it a p-d pi bond. All right. And then what we're going to do is we're going to take another oxygen here, and we're going to do the same thing. An sp2 is going to come over here, form one of the bonds, and a p is going to come over here and form the second bond of the double. And so we end up with 2 pd pi bonds. So when we look at sulfuric acid, one of these is going to be a PD. The other is going to be a sp2, sp3. The situation is we need to make two PD pi bonds at what angle? What's the tetrahedral angle? 109. So we need two PD pi bonds at 109-degree angle. There's a problem. This problem didn't occur with OPCl3. It's going to occur for this, though. And so what is that problem? That problem is this. Let's take a look at the d orbitals now. We haven't spent much time looking at d orbitals, but we're going to do it. 4 of the 5 d orbitals are shaped like 4-leaf clovers. And so this is going to be a d orbital in the xy plane. You see it's between the axes here. So we call this the dxy. It's the d orbital in the xy plane. Then we'll have a d orbital in the xz plane. And so the d orbital in the xz plane, get a different color. Will be between the axes. So this is going to stick out here. This is going to stick out here. This is going to go in. This is going to go in. So if I take my dxy and then rotate it down into the xz plane, that's my dxz. You see, they're related by a 90-degree rotation. And so in other words, they're orthogonal here. A 90-degree rotation. So you take this one and you put it flat. Does that make sense there? Okay, and then I have the dyz. And so I'll take the yz plane and then put 4 lobes in the yz plane here. That will be my dyz. I forgot to mark that. This is my dxz. And so do you see it's in the xz plane, the xy plane, or the yz plane? And those planes are all 90 degrees with respect to one another. Then we have the lobes cut between the axes, but we have one orbital where the lobes are directly on the axes. And so I'll have a lobe on the plus x, a lobe on the minus x, a lobe on the plus, oops, this is E, sorry. A lobe on the plus y and a lobe on the minus y. And so this is called the dx squared minus y squared. It's right on the axis. And then there's one more. So 4 out of the 5 orbitals are like 4-leaf clovers. And the 5th one is what we call dz squared. dz squared is along the z-axis. So I made the z-axis stick out. Maybe I shouldn't have. Let's call this the z-axis here. And so dz squared looks like a p orbital, except it has this hula hoop around it. And so this is dz squared. And so that would be along the z-axis here. So the problem comes about, it's like this. When we make a bond, we want good orbital overlap. So let's try to make a bond here between two p orbitals, a sigma bond between two p orbitals. We can either make a pi bond or a sigma bond. If we make a sigma bond between two p orbitals, then we want to overlap the two p orbitals head on like that. You see that? And so we get good orbital overlap here. And so let's say this is atom A, this is atom B, we get a nice bond like that. But what happens if they're not oriented correctly? What happens if one is like this? Here. So rather than make a bond like this, we make a bond that's kind of kinked. There's a kink in your bond. Are we going to get as good overlap here? Is it going to be as good? No. And so having a kink here, this is going to weaken the bond.
That's how the wax are.
I'm sorry? All right, so let's take a look at sulfuric acid here. So I'm going to make one double bond straight up here to the oxygen. And then I'm going to make another double bond here, 109. It doesn't matter. They're all the same, you know. So this might look different, but actually everything's the same. So if I move this double bond here, it's the same. If I move it here, it's the same. They're all at 109. So let's just look at the dp pi bond here. So I'm going to kind of do it in profile. So let's say I have, actually, can I do this one like this? Yeah. So that's one of my PD pi bonds. The other PD pi bond I need to make at a 109 angle. Do I have a d orbital that's going to be at a 109 angle? No. The d orbitals aren't oriented at a 109 angle. The d orbitals are oriented at 90-degree angles. And so am I going to get good overlap or am I going to get poor overlap? I'm going to get poor overlap because how should I arrange this? If this were one of them, how should I arrange this? Maybe here? Anyway, I need to make two PD pi bonds. And what's going to happen is they're going to suffer due to the poor overlap because they aren't oriented at 109 angles. So maybe I'll just make both of them kink, like this, to come up with some compromise. Or maybe I'll make one perfect and the other one kink severely. You know? And so the problem is that the d orbitals are not at tetrahedral angles. Are not at tetrahedral angles. Well, tetrahedral angle is 109. Therefore, we expect poor overlap. So we need some more theoretical studies in order to describe what's happening with bonding here. And so somebody did some recent theoretical studies, recent being, textbooks are always like 15 years behind. The most
50 years?
15 years.
That's totally fine.
Most of them are like, sometimes they're more up to date, more current, like 5 years. And so, let's do one more example before I talk about the theoretical studies. Another example will be this, ClO4 minus, what do we call that?
Perchlorate.
Perchlorate. Let's do the Lewis structure for perchlorate. Oftentimes with Lewis structures, I don't even bother totaling up the electrons. I just try to make a structure and then count the electrons to see if it matches. Also the formal charges to see if it matches. Complete the octet. In this, I could do it. It's probably easier to count up the electrons. So let me go ahead and count the electrons. Chlorine has 7 electrons, and then 4 oxygens. 4 times 6, 24. And then I have a -1 charge, which is 1 electron. So I'm going to end up with 32 electrons. I look at this structure over here. How many have I used up? 2, 4, 6, 8 times 4 is 32 electrons. So I'm done. I don't have any more electrons. All right, let's take a look at the formal charges. What are the formal charges on the oxygens? One, 2, 3, 4, 5, 6, 7. All these are -1. What's the formal charge on chlorine? +3. It's supposed to have 7. It only ended up with 4 in the structure. +3. Those are very high formal charges, aren't they? They're very high. And so people don't like it. And so what should we do? Yeah, we should double bond. In fact, we could get rid of most of those formal charges. And so the structure you see on Google the most, or Wikipedia, or whatever, is going to have how many double bonds?
Professor, I think your thing might have died. It's not moving anymore.
It's not moving anymore. Yeah, it died. I guess I need to charge that. Testing. I guess it's still recording. I'm going to stop it.